Hello, everyone. Hello, good morning. Let's start. Today, I'm going to talk about chapter 14. About integrals. So it's kind of the higher dimensional version of integrals. So it's called multiple integrals. And it's related to integrals of functions of several variables. So here we are going to see a few things in this chapter. For example, how to compute so-called area of some higher dimensional objects. So maybe I can write, we would see how to compute higher dimensional area using multiple integrals, or volume of solid region, or volume. And specifically, we would see double and maybe triple integrals. So let's start. So the first thing we should talk about is iterated integrals. So suppose we have a function, say f of x and y. It's a function with two variables, so it's function from R2 to R, okay? Suppose we don't know what f of x and y exactly is. The only thing which we know is if we take derivative of this function with respect to x, the result is 2xy, okay? And now the question is, what is f of x and y? Well, as you know, integral is kind of like the antiderivative, right? So if we have derivative of a function with respect to x, and we want to find out what is the function itself, it kind of makes sense to take its integral. But here, the important thing is that we have two variables. We should understand with respect to which variable we want to take integral. So here, since the derivative is taken with respect to x, the integral we should take the integral with respect to x too. So here we know derivative of the function f with respect to x is equal to 2xy. And I want to know what f is. I should take integral of this derivative. I should take the integral of this function with respect to x. So this is the x here shows the variable of the integral. When I have dx here, it means I'm taking integral with respect to x. Okay. And derivative of the function f with respect to x, I said, well, we know it is 2xy, so it would be integral of 2xy dx. Now, just like taking derivative, you remember when I told you when we have different variables, when we are taking derivative with respect to one of them, we assume the other variables are just constants, right? We would assume the other variables are just constant numbers. That's exactly the case here. When I'm taking integral with respect to x, I assume other variables are constant numbers. Okay. So here, the variable is dx, and I'm assuming y is constant. Okay, so now here, I should take integral with respect to x, so I would assume y is constant, right? So when we have a constant number, we know that constant number, it comes out of integral, right? I can just write that number in front of the integral. Here 2 is a constant, y is also a constant. So both of them come out of integral. You know, whenever we have a constant number, it just comes out of integral. Here it would work for 2 and also would work for y. So I just have integral of x. And integral of x is x squared over 2 plus a constant. But here is the only difference. So I should say plus a constant, but remember, right now with my approach, even y is a constant. So this constant might be a function of y itself. So the constant of the integral, you know, whenever we are taking integral, at the end we would add plus constant. This constant might have terms in terms of y in that thing, because we are assuming y is also a constant, right? So for example, you know, when y is a constant, y squared is also a constant. Cosine of y is also a constant. Actually, anything in terms of y is a constant. You see, so when y itself is a constant, anything in terms of y is also a constant. So here, if I multiply everything, I would get x squared y plus 2y cy. But the point is that cy is a function of y. 2y is also, well, it's something a function of y. The whole thing is still a function of y, and I need to compute that. I need to find what c is. So what is c? Right? I need to find what c is. You see, at this point, I don't have any further information. Here, I can't really compute what c is. If I want to know what the function c really is, I need to know a little bit more. So here, there is no way for us to find out. The best thing we can say is that our function looks like x squared y plus a function in terms of y. Okay, so here we don't have the information to find c. We need more information. The question should give us more things to decide about that. So maybe I would write one more thing. So for example, suppose, okay, so suppose we have a function, that is true. So, okay, someone has I got 2 comments, both of you are correct. Specifying that if you're taking integral with respect to y, cy is a constant, 2y is also a constant. So their multiplication again would be a constant. So, well, not a constant, but a function of y. I can show it with maybe not c prime of y, but say d of y. That is correct. So the final answer for me here would be f of x and y is equal to x squared y plus something which is only a function of y. The only thing which I know about d here is that there is no x in this function, right? That's the only thing which I know. Now, if the question tells me we have a function f from R2 to R such that the derivative of f with respect to x is 2xy, right? And derivative of f with respect to y is, well, let me think for a second. So the point is that we need a little bit more information. So let's say a derivative of f with respect to y is x squared plus 4y. And now we are looking for the function f of x and y. Now that's the question. Okay, so again, we would continue, we would do the same thing as I did before. We would say, okay, I'm looking for f of x and y. I know I should take integral of this derivative of f with respect to x. I should take integral of that with respect to x. So it would be, well, as we did before, it would be integral of 2xy dx. So 2y comes out, it would be integral of x dx. Integral of x is x squared over 2 plus some constant in terms of y. And if I multiply the whole thing with 2y, I would get x squared y plus 2y cy. 2y cy, the whole thing is a function of y. I showed with dy. Therefore, f of x and y is equal to x squared y plus dy. Now, let's use the further amount of information we have. The question says, if I take derivative of f with respect to y, I would get x squared plus 4y. Let's take derivative of this function we have with respect to y. So I would take derivative of f with respect to y. It means I should assume x is a constant. Therefore, x squared is a constant. So when I take derivative of f with respect to y, I have a constant x squared times y. So the derivative would be x squared plus, and then I'm taking derivative of dy. So it would be derivative of d with respect to y, right? D is a function of y. I'm taking its derivative with respect to y. And the question tells me derivative of f with respect to y should be x squared plus 4y. This simply means, well, I can cancel x squared from here and x squared from here. So it simply means derivative of d with respect to y is 4y, right? Now, I want to use this to find d. Okay, so here I have derivative of d with respect to y. In order to find d, I should take integral of this function, 4y. With respect to what? Well, here I have derivative with respect to y. I should take integral with respect to y. What is derivative of 4y? Well, it's derivative of y is y squared over 2 plus a constant. But now the question here is, does this constant c, does it contain x? Because I'm taking integral with respect to y. So I'm assuming y is the variable, so everything else is a constant. Therefore, x is a constant. So when I write c here, it might contain x. Am I right? Am I right or not? That's the question. So the question is, does C include terms? Does it include terms like x or x squared or things like that? Or it's just a constant? The point is that it doesn't. Well, it's really an honest constant. Why is that? Well, let's go back here. When we were computing f of x and y, I said, well, how did I got to d, right? When I was computing f here, I took integral of derivative of f with respect to x. And I told you that here, when we are taking integral of x, it would be x squared over 2 plus a constant, where this constant only contains terms of y. There is no x in it. And later I multiplied by 2y. So there is no x in d. There is no x in d. Therefore, when I'm computing d here, there shouldn't be any x in it. So this c here is really a constant. It's really a constant number. It's just like 2, 4, something like that. So if I do the multiplication, I would get 2y squared plus 4 times the c, which again, 4 times a constant is a constant. I would again show it with c, or I don't know, maybe with e. Now I can combine these two things to get the function f. So here, what I know is that f of x and y is x squared y plus dy. So it tells me f of x and y equals x squared y plus dy, where dy itself is equal to 2y squared plus e. Now, I can't really know for sure what is this constant, unless, for example, there is one extra piece of information in the question. So, for example, if I knew, for example, if it was part of the question that, say, f of 0 and 0 equals, I don't know, say 1, if this thing was also a part of the question. So, suppose this is also given in the question. If I knew also that, I could compute e. I could say, okay, f of 0 and 0 is equal to e. The question is telling me f of 0 and 0 is 1. Therefore, e is equal to 1. And that would completely describe, that describes f. It would be x squared y plus 2y squared plus 1. So that's how we can use integral with respect to different variables to identify a function which we have its partial derivatives. Okay, so sometimes we have partial derivatives of a function and we want to know what the function is. Okay, let's do another example. So as I said, sometimes you take integral with respect to one explicit variable. That was just the motivation. So for example, I might have x squared y cubed plus, say, x y squared. When I'm taking integral of this thing, I should know if I'm taking integral with respect to x, or I'm taking integral of this function with respect to y. If I'm taking integral with respect to x, I'm assuming y is a constant. So here, well, I can break this integral into 2 pieces, first of all. So one important thing here is that maybe when we were writing integrals in one variables, a lot of times we might not really write if this dx here, right? Sometimes we're just writing integral of x squared y cubed. But now it's really important and essential to write dx because it might be dx, it might be dy. Okay, so here we are taking integral with respect to x, so y is constant. So y cubed is constant, it comes out of integral. So we get integral of x squared dx plus. And here again, y is constant, so this y squared comes out of integral. Now, integral of x squared is equal to x cubed over 3 plus a constant, but again, this constant might depend on y because y is a constant here. So it would be a function of y plus y squared times integral of x is x squared over 2 plus another constant. Again, here, this constant might contain y. So here C1 and C2 are 2 functions which they might have y in them. Okay. So, but let's look at the second one. In the second one, the variable is y, right? Therefore, x is a constant. So I first break the integral into 2 pieces. And because x is a constant now, it comes out of the integral. And then integral, I can take integral of y plus a constant. I would show it with d1. But again, here, the integral is something with respect to y, so this constant might contain x, because I'm taking integral with respect to y. X would be a constant, so this constant indeed might be a function of x. Okay, same thing goes for the second integral. Okay. So now sometimes our integrals, they have bounds. We have explicit bounds. For example, we are taking some integral like 2x squared y squared, say dx. But we have explicit bounds. We know x, for example, goes from 1 to y. Okay, what is that? Now I want you to compute this one. So spend a few seconds to think about it and write down the answer for yourself. So here I'm taking integral with respect to x. So I would assume y is a constant. So I'm taking integral with respect to x. That's the variable of the integral, which means I would assume y is like, y behaves like a constant. Right? So it comes out of integral. It would be y squared integral of 2x squared dx from 1 to y. Also, well, 2 itself is a constant, so 2 comes out of integral 2. Now I have integral of x squared, right? Integral of x squared dx. So I would get x cubed over 3 plus a constant. But again, remember, this constant might depend on y because, well, y behaves like a constant here. And then the values should change from 1 to y. So it means once I should let x to be equal to, y. Remember, these values, they are values for x because we are taking integral with respect to x. So the numbers here means we should plug in these numbers into the variable x, right? So I should let first x to be this number x, then I should let x to be this other number 1, and then I should subtract them. So first I would get 2y squared. I should plug in y, the value of y here, so we get y cubed over 3 plus 3y minus, now I should let x to be 1, so it would be 2y squared over 1 over 3 plus cy. Okay, and now I should subtract them. So I would get 2y to the 5 over 3 plus 2y squared cy minus 2y squared over 3 minus 2y squared cy. Now the good thing is that although cy is a noun for us, we don't know what cy is, but they really cancel each other, these two terms. So we end up with 2y to the 5 over 3 minus 2y squared over 3. That's the final answer. Now it's kind of interesting. We can kind of mix these integrals. So maybe as the second example you can think about is that suppose we have a combination of these things. We have 2x squared y squared plus, say, 3x. We have this function. Suppose we take first integral with respect to x, okay? And suppose x changes from 0 to, say, y. These are the bounds for x. And after that, after taking integral with respect to x, we can take another integral, just like we can take a second derivative, we can take a second integral. with respect to y now, and suppose the value of y changes from, say, 0 to 1. Now, what is that? Okay, think about this one for a few minutes, and then I will solve it for you. Okay, we already have a guess for the answer, 2/15. Let's see. Okay, so first, it means first I should take integral with, another answer, 11/18. So first we should take integral with respect to x. We should start with the innermost one, you see, from this one. So first, the first step is to compute this integral, 2x squared y squared plus 3x. But I should take this integral with respect to x, 0 to y. Okay. So I would break this one into two pieces. It would be the integral of 2x squared y squared from 0 to y dx plus integral of 0 to y 3x dx. Okay, here x is the variable and therefore y is the constant. Therefore, y comes out of integral, just like any constant number. So here we would have 2y squared. They come out of integral. So I should only take integral of x squared dx from 0 to y plus. Same thing is true for 3. 3 comes out of the integral. So it would be 3 integral of x from 0 to y dx. Okay. Now I should take derivative of x squared, which is x cubed over 3 plus a constant. But again, here the constant might contain variable y, because y is like a constant when we are taking derivative with respect to x. So that would be the integral. And then we should plug in y and 0 and subtract them. Plus. And the integral of x is x squared over 2. And then again, there might be a constant. The constant might depend on y. Again, we should plug in y and 0 here. Again, remember that these numbers, y and 0, they are values for x. We are taking integral for in terms of x. So these numbers, they are values for x. So let's plug them in. So here we get 2y squared, x cubed, which instead of x we write y, it would be y cubed over 3 plus c1 of y. And then we should subtract 2y squared. Now we should plug in 0. So it would be 0 over 3 plus c1 of y. Plus 3x squared over 2. It would be y squared over 2 plus c2 of y minus, and then we should plug in 0 here. So it would be 0 squared over 2 plus c2 of y. Okay, some of these things cancel each other. So as you can see, c1 cancels with minus c1, c2 cancels with minus c2. That's a good thing. So if we do the multiplication and simplify it a little bit, we would get 2y to the 5 over 3. And well, we have 0 there, and then we get 3y squared over 2. So this thing is the result of the inner integral, but there is another integral left, right? So I should take integral with respect to y now. Okay, so I have this function plus 3y squared over 2. Now I should take the integral. Yeah, the constants here and well, kind of always cancel each other. That is true. So when we are entering these kind of values for the integral. So now I should take another integral with respect to y. There is another integral left, right? I should compute the integral with respect to y. So I should take integral of this thing with respect to y. Now, the important thing is that when I'm taking integral now, remember, there is no x anymore here. And when at the end, when I'm taking the integral, I would always plus a constant c. That c does not contain x anymore. Although here it doesn't matter, they would cancel each other, but we are done with x. You see, we took integral in terms of x. Whenever you take integral in terms of each variable, you are done with that variable, right? There is no x here anymore. Okay. So we should take integral in terms of y. It would be 2 over 3. Integral of y to the 5 is y to the 6 over 6 plus 3 over 2. Integral of y squared is y cubed over 3. And then we should plug in 1 and 0 and subtract them. It would be 2 over 3, 1 over 6 plus 3 over 2, 1 over 3. And then we should plug in 0 here, which makes everything 0. This is equal to 1 over 9 plus 1 over 2, which is 11 over 18. If you gave this answer, that's good. Yeah. So that's pretty good. That's how we compute these iterated integrals in terms of different things, different variables. Okay. Now we can move on to the second subject. The second thing, so we started with iterated integrals. Now we have the necessary tools to compute area of a region. So, well, this is something which you might have seen before. If you have, say, the plane R2, which we can show it with X and Y, there might be some curves give you an area, right? And so let me show it like this. There might be some curves which they give you some region in the plane. So for example, you have a function f, and then you have another function g. And you already know from like, well, I mean, but you already know, I mean, it can be computed using single variable calculus. What is the area of the region between these two functions? Now, we can use iterated integrals to compute regions bounded by the graph of functions. Let me give you so the idea is to compute the area, for example, of this blue region. What is the area there? Let me give you one explicit example. This is a good example. It's an example of the book. Suppose these two functions, f of x equals sine of x, and g of x equals cosine of x. Okay, so one of them is sine is, well, I would show it with red. Sine is like this, and it would continue, right? From both direction. Cosine is like this. Etc. So there are some points. There are some points which they would intersect. One of these intersections is pi over 4. This intersection here, you see the graph of two functions intersect here at this point. This point is pi over 4. We know that, right? Sine and cosine of pi over 4 are equal. Sine of pi over 4 is equal to cosine of pi over 4, which means they intersect. Whenever they are equal, it means they intersect. This is square root of 2 over 2. Another place which they intersect is, well, here, as you can see, and this is 5 pi over 4. Sine of 5, well, it's interesting. Sine of 5 pi over 4 equals cosine of 5 pi over 4 equals, does anyone know what is it equal to? Sine and cosine of 5 pi over 4? Yeah, that is true. Negative square root of 2 over 2. Correct. Now, between these 2 points, between these 2 intersection points, there's an area, there's a region bounded by sine and cosine. Look at this region. Okay? There is a region bounded by these 2, the graph of these 2 functions. Now we can use this method of iterated integrals to compute this area. We can use this to compute this area, to see what this area is. So actually you have seen, as someone has mentioned in the comments, there was another way we could compute this region. The way I'm going to introduce now is probably new to you. So another way of computing regions is that I can take integral of, well, double integral of 1, say dy dx. I should just write down, well, the first integral is with respect to y, the second integral is with respect to x, right? I should just write down I can change the order doesn't matter. It can be dx dy or dy dx. I should write down what are the bounds for x and y. That's the only thing which matters here. So for example, look at the value of y. The value of y shows this coordinates, right? This shows this axis, the red axis. Can you tell me what are the values of y? If I look at these green points, look at this green region here. Look at the points there. Every point there, every point inside this green region has some x and has some y. The key in solving these questions is to find how x is bounded and how y is bounded. What are the bounds for y and what are the bounds for x? So here, what is the maximum thing y can be? Y can go up until it gets to the red graph. But what does the red graph represent? So as you can see, any point in this green region is below the red graph. That is correct. Any point in this green region is below the red graph. So any point there, if you look at the y coordinate, if you look at the y component, is less than sine of x, because that red thing is sine of x. And any point in this green region is above the blue graph, right? It's above the blue graph, but the blue graph is cosine of x. So y is between cosine and sine of x. Okay. What about x? What are the bounds for x? Well, as I said earlier, x can be between pi over 4. It starts at pi over 4. It goes until 5 pi over 4, right? This is pi over 4 here, and this is 5 pi over 4. The value of x goes from pi over 4 to 5 pi over 4. So I would write down these boundaries here for this integral. So y, the boundaries of integral are cosine of x and sine of x. for y are pi over 4 and 5 pi over 4. And the result of this integral is the area of the green region. Well, let's compute that. Okay, first we should take integral of 1 with respect to y. What is integral of 1 with respect to y? Well, it's simply y itself plus a constant. So y plus a constant. But when we are supposed to plug in these things, as you saw before, the constant would cancel. So I wouldn't even write plus a constant. It's just integral of 1 with respect to dy is y itself. And the bounds are sine of x and cosine of x. Right? So that's the inside, the integral I have on the inside. So I should plug in these two things. I would get sine of x. I should plug in sine of x instead of y. And then I should plug in cosine of x instead of y. I should subtract them. Well, I would simply get sine of x minus cosine of x. Now I should take integral of this thing with respect to x from pi over 4 to 5 pi over 4. Well, integral of sine is minus cosine of x, minus integral of cosine is sine of x. And the bounds are 5 pi over 4 and pi over 4. I should plug in these two things. Cosine of 5 pi over 4 is negative square root of 2 over 2. So there's another minus sign here. That's what I would get. Plus square root of 2 over 2 minus, and then I should plug in pi over 4. It would be minus square root of 2 over 2 minus square root of 2 over 2. The result is 2 square root of 2. Now, there are a few things to note here. There are a few important things. When we are like computing the area here, I said what is the bounds for y, what are the bounds for y, what are the bounds for x. So here our first variable is y. I decided to take the integral with respect to y first. I could change them. It's okay. I could change them. I could take integral with respect to x first and then y. Both of them are correct. Sometimes one might be easier than the other one, okay? Now, what's the difference? The difference is that when you have your first variable, here y, the bounds can be in terms of the second variable. The bounds can be in terms of x. But when you are dealing with your second variable, the bounds shouldn't be anything in terms of the first variable anymore. They should be constant numbers. They can't have y in them anymore. They can't have x in them anymore. Let's look at another example. So let's just look at one more example of this thing. Suppose we have this function. Suppose we have this function f of x equals x squared and g of x equals square root of x. Okay, so this is x squared. That's how the function y equals x squared look like. And this is how the function y equals square root of x look like. I'm just looking at the positive side. Okay, they intersect at 2 points. So what are the intersection points? Intersection means they're equal. It means x squared is equal to square root of x, right? One intersection point is here. It's obviously 0. There is another intersection point here. First, I should find out what is the other intersection point, and then I want to compute the area of this green region. Okay, so what is the other intersection point? I would let these two functions to be equal. I would get x squared equals square root of x. I can square both sides. I would get x to the 4 equals to x. Well, it means x to the 4 minus x is equal to 0. it means x times x cubed minus 1 equal to 0. Either x is 0 or x cubed minus 1 is 0, which means x cubed is equal to 1. Over the real numbers, it means x is 1. So this other point is 1. And I want to know what is the area of this green region, okay? I should take integral of 1 dy dx, okay? Now, again, I'm the person who decides if I want to write dy dx or dx dy. The order does not really matter. I mean, one might make it easier, the other one might make it harder. Again, I prefer to write dy dx. Usually for this case of, well, I mean, here it's completely symmetric. It really doesn't matter. Now I should decide about the bounds. What are the bounds for y? What are the bounds for x? If my first variable is y, so y is the first variable, but what do I mean by first variable? I mean, I take integral with respect to that first, and then it comes, the turn of the x comes. After taking integral with terms of y, I take the integral in terms of x. So first y and second x. In the first one, y can depend on x, the bounds of y. So the bounds of y can depend on x. When I get to my second variable, the bounds should be only constant numbers. Okay, here. So let's look at the point here. Take a point in this green region. What are the bounds for y? If I go up, I would get to this red curve. So the y value of this point in this green region is less than y value of this red curve. But this red graph, this red function is the square root of x. So it means y is less than square root of x, right? If I come down from this black point, I would get to this black graph of function. This is x squared, right? If we are above x squared, it means y is greater or equal than x squared. Now, what are the bounds for x? Well, as I said, here we only accept constant numbers. Of course, x is between 0 and 1. Yes, that's correct. So when we are taking integral, dy goes from x squared to square root of x, and x goes from 0 to 1. We should take this integral. So we should compute the integral of 1 dy dx plus x squared to square root of x and plus 0 to 1. Okay, first we compute this integral in the inside, the innermost one. It's integral of 1, right? Integral of 1 dy from x squared to square root of x. Well, integral of 1, when we are taking integral with respect to y, is just y. And the values here we have are square root of x and x squared. It means first, instead of y, I should plug in square root of x. Then instead of y, I should plug in x squared, and I should subtract them. So it's a square root of x and x squared. And then I should take integral with respect to x and plug in these numbers. So what is integral of a square root of x? Well, square root of x is x to the power 1 over 2. Integral of x to the n is, well, 1 over that power here, 1 over 2 plus 1, x to that power plus 1, minus the integral of x squared is x cubed over 3, and then I should plug in the numbers 1 and 0. Okay, so what is this number here? This number is 3 over 2, 1 over that is 2 over 3. So it's 2 over 3, x to the power 2 over 3 minus x cubed over 3. Oh, sorry, the power here is 3 over 2. From 1 to 0. So it would be 2 over 3 times 1 minus 1 over 3 minus, then I should plug in 0, which is 1 over 3. So that's the area of that green region we had between the two functions, square root of x and x squared. Any question here? Okay. So that's the section 14.1. We finished the first section of chapter 4. Let's have 10 minutes, 12 minutes break. Let's come back, say at 10:15. We would start with the section 14.2. We would talk about volume. Now we talked about area. The next step is to talk about volume. Okay, let's have a short break.